Hello everybody, I am Dr. M. Shobana, Associate Professor in the Department of ECE. In this video lecture, I'll be explaining the basic concepts of electromagnetic fields. The first topic that I'm going to cover is physical interpretation of curl, gradient, and divergence. Before we actually get into curl, gradient, and divergence, let us understand what is the del operator. The del operator, as we all know, is the differentiation operator. Del is also known as del or Knapp law, and it has many applications in physical problems. Del is actually defined by dou by dou x I vector plus dou by dou y along j vector plus dou by dou z k vector, where I, j, k are the unit vectors along the direction x, y, and z. Now there are three possible operations with del corresponding to the three possible types of vector multiplications. Now let us consider that if f is a scalar function, then we can define the gradient of that function by del f. So we actually define del f is equal to gradient of f, where the gradient of the function f is given by dou f by dou x along the vector x cap plus dou f by dou y along the vector y cap plus dou f by dou z along the vector s cap. Now let us see what is divergence. Now if v is a vector function, then we can define the divergence of v as del dot v. So del dot v is defined as divergence of v is equal to dou vx by dou x plus dou vy by dou y plus dou vz by dou z. Now coming to the curl, suppose we are given a function, vector function v, then the curl of that function is defined as del cross v, which is equal to del cross v is nothing but the determinant of x, y, z, dou by dou x, dou by dou y, dou by dou z, and vx, v by vz. Now we actually move into the physical interpretation of gradient, divergence, and curl. Having seen what are gradient, divergence, and curl, now we'll see the physical interpretation of gradient, divergence, and curl. Gradient of any scalar function is the maximum space rate of change of that function. Now suppose if f represents the temperature, then del f is equal to gradient of f is the temperature gradient or rate of change of temperature with distance. So if v is a scalar quantity, but del f is a vector quantity. So the gradient of f can be defined as dou f by dou x along the vector x cap plus dou f by dou y along the vector y cap plus dou f by dou z along the vector z cap. Now coming to what the physical phenomenon that we see in our day-to-day life. So to understand divergence and curl, let us study about the fluid motion. Now, in practical example, divergence is the netward outward flow of liquid in all three directions. Now, take for example, the first diagram here shows the divergence. The arrow pointing outwards shows the divergence, whereas the second diagram shows the convergence. And all these phenomena can be used to study the fluid motion. Now this second graph denotes the convergence, and in practical situation when we want to study the fluid motion, we come across this divergence. Coming to the curl or rotation of a vector quantity can be best understood by stream flow. Now what is actually a curl? Now the curl is nothing but the rate of rotation or angular velocity at any point is a measure of the curl of the velocity of the water at any point. Now, in this case, where we see the rotation is about the z-axis, the curl of V is in the z direction, and any curl can be represented by del cross V along z direction. Now, a positive value of del cross V along z direction denotes a rotation from x to y, that is, in a counterclockwise direction. So we can understand that a positive value of dou Vy by dou x will tend to rotate any structure, that is a leaf or any disk, in the counterclockwise direction, whereas a positive value for dou Vx by dou y will tend to produce a clockwise rotation. So we can see that the rate of rotation about the z-axis is therefore proportional to the difference between these two quantities. Now, if we want to take another example for curl, suppose here we consider a pond, and I am going to immerse a disk. Now you can see that there will be a whirling motion of the disk in a pond. Now the pond try to rotate in anti-clockwise direction, as I have indicated here. This arrow, the arrow points downwards. In the next diagram, you can see that the disk rotates in anti-clockwise direction and the arrow pointing in the opposite direction. And in the third diagram, we see the disk rotating and where the arrow points in the upward direction. So the whole phenomena, we can see that the disk rotates in anti-clockwise direction. So the movement of this disk represents the curl phenomenon. So that's all about in this video lecture. Thank you.